I'm going to walk you through the mock paper you did this year, 2024 mock. We use, as you can see, probably underneath the TEPEX here, the paper that was published in 2020. 2020 was a pandemic year, so it wasn't sat in May by people, but was used in autumn for people that weren't happy with their grades. This was a paper that was used. I took out 45 minutes of questions, and I also added a question from paper 2, as you'll see towards the end. So I didn't use all the questions, but it's a good idea of the kind of things you'll get in a GCSE chemistry paper. Right, the paper was tough, I thought. I thought it was quite difficult, and that's a good challenge for you at this stage. Right, so there's a lot in the first question about structure and bonding. This is one of the most important topics. I would really encourage you to spend time getting your head around it, studying and learning. We've got to get the head around what we mean by intermolecular forces. This comes up a couple of times in this first topic. So intermolecular forces is a force of attraction that happens in between molecules. In between molecules. Now, molecules refers to substances that are bound using simple covalent. So an example would be one of these on here. Standard example might be something like water. So that's a water molecule made of 2 hydrogens and 1 oxygen joined together with covalent bonds. So there's a bond between the hydrogen and oxygen and the other hydrogen. But the reason that water is a liquid at room temperature, for example, or a solid below 0, is there are weak forces between the water molecules which can be overcome if you heat the water up, but they are relatively weak, much weaker than covalent bonds. Covalent bonds are the lines we draw between the atoms. Okay, really important idea. If you're finding this hard and difficult, you must get your head around this. Talk about it with your teacher before too long. So water's one of them. I thought it was a much harder question to get the other one, which was polyethene, and I'll talk about that in a second. But you can work through the others and recognise that by process of elimination it had to be polyethene. So diamond is giant covalent, magnesium is a metal, sodium chloride is giant ionic. So it had to be polyethene for that reason alone. But if you think of a polymer as like wet bits of spaghetti or cooked bits of spaghetti in a pot, they're long molecules, long chains of molecules. We'll study these in much more detail in the back end of year 2, year 11. There are weak forces between those long polymer chains, and that's what's going on there. So I'm not too worried if you didn't get that for now, because we'll do a lot more on polymers next year. Then what you have to do for the main bit of this question was discuss the bonding and structure of 3 compounds. Okay, so there's lots and lots of things you could have said here to get the marks. Exactly how the marks were issued by the examiners is very difficult to predict, so we've done our best to be consistent with marking. But I wouldn't overly worry about your score or what you got compared to a friend, let's say, but I'd be more concerned about thinking about what you should and shouldn't know about this idea, because these are very common questions. Okay, so let's do them one at a time. So carbon dioxide, the picture of it was given to you in your paper. It looked something like that. These lines are representing strong covalent bonds. We know it's covalent because this is a non-metal and this is a non-metal. So there are strong covalent bonds between the atoms. Right, so people are using vague terms like molecules or ions or whatever, but these are atoms that have been joined together. You might have said in your answer what a covalent bond is, or you should have done. So it's a shared pair of electrons. And you should have said really these are double bonds as well. So there's 2 shared pairs of electrons between the oxygen and the carbon, and that carbon and the oxygen there as well. So mentioning their non-metals was worth noting. They're both non-metal atoms, which is what the clue that it was simple covalent, and these are what we call molecules. Okay, so there we are. So therefore they'd have intermolecular forces between them. And people again were pretty unclear about this. The intermolecular forces were between the molecules, in between one carbon dioxide and another. So just like I did in the previous page, CO2, CO2, CO2. When CO2 turns from a solid into a gas, as it does if you heat it up, dry ice, which is what this stuff is when it's very cold. If you heat it up, the very weak forces between the carbon dioxide molecules break. Okay. So that's carbon dioxide. You've got magnesium oxide The structure of that's given on the picture. It looks like this. This is a lattice of oppositely charged ions. And really you should have got that. It was given to you in the question. The ions are labelled with charges, the atoms are not labelled with charges. So these are ions, and we could give you some credit for that, but really it was given to you in the question, so not too much. But you should have been clear that it was a giant structure because it goes on infinitely in 3 dimensions, and it's a lattice, described as a lattice structure, which is this arrangement of oppositely charged ions, so plus minus, plus minus, plus minus, plus minus, over and over again in 3 dimensions for gazillions of ions. Okay, should be clear the magnesium is 2 plus oxide 1 minus, which was given to you in the question. And we knew it's ionic because we've got a metal and non-metal, metal and non-metal. And my classes have seen this, but it's a nice way to show people that metals make positive ions if you can't work it out when you're under the stress of an exam. Metal's got a plus in the middle of the word if you write it like that, and non-metal's got a minus in the middle of the word. So if you've got a metal and non-metal, you'll find you get a plus and a minus. Really easy to work out which one's which. So you get credit for saying it's a giant structure, it's a lattice structure, and you get credit for saying that the ionic bonds are strong again. Some of you went on to explain then that meant it had high melting point, but you didn't need to do that. It wasn't worth any marks. But you were expected to talk about how ionic bonds formed, which is where there's a transfer of electrons. Ideally, you should say 2 electrons from magnesium atom to an oxygen atom to make a magnesium ion and an oxide ion. You should be talking about that. Lastly, silicon dioxide. Again, it should be clear from the picture that these are atoms because there's no charges on them, and it should be clear that this is a giant structure. Again, you've got this very large 3-dimensional structure goes on in every direction or 3 dimensions if you like, for a long way. So SiO2, 3D giant structure. It's very similar, the structure to diamond, and if you know the structure of diamond and look at how the silicon atoms are placed, they're set up in exactly the same way as in diamond. You should have identified the fact that it's covalent bonding again because it's non-metals. You've already said what a covalent bond is up there. Covalent bonds, non-metals only. You could have talked about the fact that covalent bonds are very strong again. And you might have talked about then the properties, which you didn't have to do. You were told as examiners to ignore that. But you should have identified that they're single bonds this time though, which you could see from the picture. But the key things, the most important things I would say, giant structure, and this is did I even say it? Simple covalent structure up here. Probably the most important things to get across, and that leads then to the different properties that we know about. Okay, I'm going to do one more question.